Welcome back, students. Today we're going to get into our new material over polynomials of higher degree. So far we've studied linear functions where if you look at them, y equals x, y equals mx plus b, the graph is going to be a line. So linear functions. What makes it a linear function? Well, the x and the exponent on that x, the 1. Right there. So that linear function, any linear function, the highest exponent that you're going to have for your variable x is going to be to the first power. That's said to be a function of degree 1. And again, all degree 1 functions are linears because their graph will be lines. Then we got into degree 2, which means that you have quadratics because you have y equals x squared. Now there might be an x term with it. Okay, but the main thing, the shape of the graph is determined by the highest exponent. So the largest exponent that we see is to the second power, which makes this degree 2, and that makes it so we have a parabola. Today we're going to focus on what are called cubic functions because we're going to have x to the third power. Now we might just have x to the third power all by itself, or we might have x squared term. We might have an x term. We might have a constant. Okay, we might have all of those terms, or like I said, we might just have x to the third power. The only one that we have to have in order to have a cubic is x to the third power. This is said to be degree 3. And so what the degree 3 tells us is that when we eventually solve these equations that are of degree 3, is that we are going to have 3 solutions. Before we get into solutions and roots and x-intercepts and so on, let's look a little bit more at these graphs. So if we look at graphs that we've studied before, such as lines, or if we look at our parabolas, if we put a negative in front of that x squared term or the x term or in front of the x to the third, that's the leading coefficient. If it's positive, we have our graph that does one thing, and if it's negative, that graph will always flip it. So that's very easy to see with the parabola, where we have both of the ends of the parabola. Okay, we have it so the both ends go up, they go in the same direction. But if we put a negative leading coefficient out in front, now both arms still go in the same direction, but they go down. For a line, if we have a positive leading coefficient, we were told that that's called slope. We have a positive slope, which means the graph goes up from left to right. But if we put a negative out in front, okay, now the graph flips. Okay, all that happened was the graph flips. Instead of being down here at the negative value, now it's up at this positive value. So now the graph is going down from left to right. Notice that for a line, one side goes up and one side goes down. They go in opposite directions. And that's always going to be the case whenever we have an exponent of odd degree. Okay, so 1 is an odd number, 3 is an odd number. So notice that both of these graphs, they're going in opposite directions from one side to the other. Okay, so that's the same thing for your cubic function, x to the third power. Notice that they go in opposite directions. If we have a positive leading coefficient, it means that we increase from left to right eventually. Now, in some part in the middle, we might go back down, but overall, from left to right, we're going from low to high. We're going from this low value up to the high values. We're increasing from left to right, just like with linear. If I change that to be x to the fifth power, the graph looks a little bit different, but same end behavior. On the left side, the graph's going down. On the right side, it's going up. If I flip the graph by making a leading coefficient be negative, now it's going from up down to low. So what you're going to be doing on this homework assignment is going to be, on the first 4 questions, using Desmos. And actually, you can answer some of these before using Desmos about the characteristics of the graph, and then also graphing a sketch, making a sketch of the graph itself. So that's what you're going to do on questions number 1, 2, 3, and 4. So let me walk you through question number 1. So first thing that I'm going to do is identify what's the leading coefficient. So here we have the function f of x equals x to the third power minus 5x plus 2. It's in standard form, which means we're going from the highest exponent down to the lowest, or no exponent in this case. The leading coefficient is the number out in front. So in this case, the leading coefficient is 1. What's important about the fact that this is 1 is that this is positive. So because it's positive, that means that we're going to start low and we're going to end high. So the end behavior, this is going to be the fancy mathematical way for us to write it, the mathematical notation, as x approaches negative infinity. So that's just saying on a number line, negative infinity would be over here. Positive infinity would be over here. So on the number line, on the left-hand side, where's your graph? What's it doing? So on the left-hand side, we see that the graph is going down. So those y values, or in this case, in function notation, the f of x values are going down to negative infinity. And then as x approaches positive infinity, so on the right-hand side, what's going on? Well, those values are going up. So f of x is approaching positive infinity. Domain and range, we'll write these in interval notation. So don't forget that your domain are your x values and your range are your y values. How far to the left can we trace the graph, and how far to the right can we trace the graph? Right? Even if we don't have this graph typed into Desmos yet, okay, it's going to be the case with all of our cubics. Let me change this back to a cubic. We're going to be able to go as far left as possible, and we're going to be able to go as far right as possible. The graph is continuous, which means that it just keeps going on forever. So that means that the domain is going to be all real numbers, but writing that in interval notation, we say that we can go as far left as possible, so we can go to negative infinity, and we can go as far to the right as possible, which means we can go to positive infinity. Now, don't forget that when you're using interval notation, you can't reach infinity because it's not an actual number. It's a concept. So make sure that you use parentheses around infinity symbols, because you can't, it's not actually a number. It's not actually included in that graph. Because if it was, we could just say, hey, add one more, and then we could go even one step further. Your range is also going to be all real numbers. We're going to go from negative infinity to positive infinity, because remember, we have an odd degree polynomial, which means our arms go in opposite directions. So that means that we're always going to have one side, whether that's the left side or the right side, which is determined by the leading coefficient. We're going to always have one side that goes down and one side that goes up. So we're always going to have one going to negative infinity and one going to positive infinity. We will always, it doesn't matter if it starts high and ends low, you always start off with a smaller value followed by the larger value. So when you write all real numbers correctly in interval notation, you're always going to use parentheses, and it's always going to be negative infinity, comma, positive infinity, because you have the smaller value compared to the larger value. All right, everything else I'm going to have to get specifically from the graph itself. So now I'm going to have to go to Desmos, and I'm going to actually have to type the rest of this in. So f of x, I can type that. I can just type in x to the third power. I can just type in the right-hand side, or if I want to change this to be y equals, I could do that as well. All right, so now we have our graph. I can zoom out just a little bit, but you can see that really, if you zoom out, the only interesting part happens right in here. Okay, this is the only interesting thing that we have. Otherwise, we're just going down and we're going up, which is what we already identified. Here's the only place where we have something that deviates from that a little bit. All right, so this right here, and if you click on the graph, it's going to tell you, hey, these are the points that are your points of interest. These are the points that are going to be the main points in your graph. So that's why we're going to include them here in these blanks, but then we're going to also make sure that we sketch those in the graph below. So if you click on your graph in Desmos, it's going to always tell you the y-intercept. So all you'll need to do is click on it, and that's your y-intercept. It gives it to you as an ordered pair. Please go ahead and write it for me as an ordered pair as well. And then the x-intercepts. Again, this is degree 3. So that means that the most that we can cross through the x-axis is 3 times. We might just cross through it once. We might cross through it up to 3 times. Okay, we can't just cross through it 0 times because remember, the arms go in opposite directions. So this is getting a little bit into calculus, but what this is saying is that at some point it's going to have to cross through that x-axis if we're going from negative infinity to positive infinity, because the x-axis represents the number 0. And so to go from negative infinity to positive infinity, you have to go through the number 0. Anyway, back to algebra 2. Here we have 3 x-intercepts. All I had to do is click on them, and then now I'm just going to write them down. My x-intercepts as ordered pairs are negative 2.414, comma 0. The next one, notice I'm going from left to right, just like I read, just like I write, okay, left to right. So I'm going to do my smallest to my largest. So next I have 0.414, comma 0, and the largest one was at 2, comma 0. X-intercepts is basically a synonym to the word 0. It's just how we write them. X-intercepts, we always write those as ordered pairs, versus zeros, we just write the x-coordinate that makes it so our function equals 0. So we're just going to write down the x-coordinate of the x-intercepts. So negative 2.414, positive 0.414. And for now, we're just going to have these decimal approximations. Eventually, we're going to have to get these exact values. So because there were 3 x-intercepts, that means that there are 3 real zeros. Okay, the number of x-intercepts that we have is going to always tell us how many real roots we have, how many real zeros we have. So because we have 3 real roots, the number of roots is determined by the degree of the polynomial. So because our degree of our polynomial is 3, it means that these 2 lines together should combine to 3. So all 3 of these are real roots, which means we have 0 non-real roots. Now, relative maximum and relative minimum. We've seen the word maximum, we've seen the word minimum before, but that was talking about parabolas. What was the highest point? What was the lowest point? Well, we don't have a parabola, except what if I do this? What if I zoom in? Now I focus in on just this portion of my graph, and now it looks like I have a parabola. Okay, it's not exactly a parabola. We don't have that exact symmetry that we would with that parabola. Okay, but we do have that basic shape of a parabola in the fact that it looks kind of like a hill. So the highest point that we see in this window that I now have, this is a maximum point compared to these points around. So that's why we call it a relative maximum. Versus if it's the overall highest point, we call it an absolute maximum. So all you need to do, again, Desmos tells you all of your key points. So all you need to do is click on your graph, the point appears, and then you just need to transfer, hey, this point right here, this ordered pair, this is a relative maximum. So I'm going to write down, I'm just going to copy down my relative maximum. And then relative minimum is basically the same thing, but instead of having a hill, you're looking for a valley. So here is a point, here I have a valley. So if I look at just this window of my graph, it looks just like a parabola. It looks like I have a lowest point. I know if I zoom out, it's not the actual lowest point. So that's why it's called a relative minimum. So I'm going to write down what this ordered pair is, and now I have my relative minimum. Okay, now the only other thing for me to do is to plot all of these points and then possibly include some points in between that's going to give me the basic sketch, the basic shape of this cubic function. So what I can do here is I can look at my graph and zoom back out. And again, this is what I basically want to replicate. I want to replicate this basic shape. If I zoom out, this really isn't that important because all this is showing is that it keeps going down, and all this is showing is it keeps going up. So if I zoom in, this is really what I want to replicate right here. I need to make sure to include all of these points that I already identified up above. I need to put them now onto my graph. And then any nice integer values that fall in between is what I should include. So what I'm going to start off with is planning. Here's my highest point. Here's my lowest point that I have to make sure to include. So going from just over 6 to just below 2, negative 2, okay, I don't need to change my scale. All I need to do is decide where I'm going to place my x-axis and my y-axis. And so because I have to go up to positive 6 and go down to just below negative 2, that means I'm going to probably place my x-axis more towards the bottom. All right, so here I have my x-axis and then my y-axis. It just needed to be towards the center because I have points to the left of the y-axis, I have points to the right of the y-axis, but they're all pretty much centered about that y-axis. So now, since I already decided I'm not changing my scale, now I just go through and plot everything. So I can just go in the order that I wrote them. So the y-intercept is at 0, 2, so I'm going to plot a point at 0, 2. Oops. Then I'm going to plot my x-intercepts. So negative 2.41. So I'm going to go just past negative 2. I'm going to go almost to negative 2.5 and plot a point on the x-axis. Positive 0.414 means I'm going to go almost to the halfway point in between 0 and 1, and I'm going to plot a point. And then 2, 0 means I'm at exactly 2 on the x-axis. I also need to make sure to include relative maximums and relative minimums. So at negative 1.291 and then up just past 6, I'm going to plot a point. And then at positive 1.291 and then down at negative 2.3. Okay, so the only thing left to do now is to plot some points in between. So taking a look at these integer values, what I'm going to do is I'm going to convert this to a table of values. Negative 2.41, so if I go just to the left of that, the value would be negative 3, which is down at negative 10. If I look back at this, I wouldn't have room to graph negative 10. So I'm not going to graph the point at negative 3, negative 10. So that means I'm going to start off by plotting the point negative 2, 4. So here's negative 2. I'm going to plot a point up at positive 4. Next integer value would be negative 1. So I'm going to plot a point at negative 1, positive 6. Next integer value would be 0, which I already have it at 2. Next integer value would be positive 1, which is down at negative 2. And then the last one would be 2, which I already have. Let's see where 3 is. 3 is at 14, and I won't have enough space to do positive 14. But what's important about it is that 3, we're up somewhere up here, okay, because we're going up to positive infinity on the right-hand side. And at negative 3, we're at negative 10, which meant that we were down here somewhere. So that's going to come into play right now as I connect these. Okay, I'm not going to start randomly anywhere. I'm going to go to negative 3. Negative 10 would have been somewhere down here, so I'm just going to pick up my pencil about where it would be taking me. And then I'm going to come up. I'm going to go through. I'm going to go through every single one of these points, except I always bounce off of any relative maximums or minimums. So this was my highest point up here, which means I can't go past this point. So now I have to come back and go around and come down through these remaining points until I reach my relative minimum, which means I bounce off of it again and then I go back up. And then I'll make nice arrows to say, hey, this graph keeps going, even though I'm not going to plot those points. The arrow says it continues in this direction. So notice that this is exactly what I stated up here, that because the leading coefficient was positive, we started on the left side from somewhere down low, and we're ending on the right-hand side somewhere up high. So we're starting down low, and we're ending somewhere high. And that's all you're going to do for question numbers 1, 2, 3, and 4. Use Desmos for a lot of it. You're identifying the main characteristics of the graph, and then you're going to just work on that very important, we're going to do it a lot this semester, skill of being able to sketch a graph. Now let's go to question number 5. So 5, 6, 7, and 8, you can read through the directions for it, but these are going to be a little bit different. You can see that it starts off the same way, but rather than having a graph to sketch the graph, now we have some workspace because there's going to be some work that we do by hand. So the first thing that you're going to do, just like with the last one, is you can graph this into Desmos, but you're going to pay attention to the leading coefficient, and you're just going to identify the main characteristics of this graph. So because the leading coefficient, once again, is positive, that means my graph goes from low to high. The exponent is odd, which means they go in opposite directions. And so because they go from low to high, what this is saying is my f of x values on the left-hand side go to the low value. They go to negative infinity. and my f of x values on the right-hand side go to positive infinity. My domain and range will always be all real numbers for any cubic that I have, so from negative infinity to positive infinity. Now these other values I'm going to need to get from Desmos. So give me a second and I'm going to graph this. So I typed it in, x to the third power. Like I said, it's going to start low. So if I look on the left side of this, notice I'm going down. And if I trace this on the right-hand side, it goes up. This isn't nearly as interesting as the last one was. There aren't any relative maximum or minimums because I don't see any of those hills or valleys in my graph. Okay, there is a little switch of something that in calculus you'd find out is called concavity. Okay, but overall, there's really not that much that's that exciting that's happening with it. Only important points that if I click on Desmos that it tells me, it's going to be the y-intercept, and this one only has one x-intercept. So I'm going to start off with the y-intercept, which is at 0, negative 12, and the x-intercept, which is at 1.5, comma 0. Now, the number of solutions that you have to a polynomial equation should be equal to the degree of the polynomial. So this polynomial is degree 3, which means that there should be 3 solutions. There should be 3 zeros. How we got our last zeros was just by looking at our x-intercepts. We had 3 of them. But in this case, we don't have 3 x-intercepts. We only have 1 x-intercept, which means there is only one real zero. The key word right there is real zero. There's only one real zero. There's only one real root, which means since there have to be 3 of them, we're going to have 2 non-real roots. We're going to have 2 non-real zeros. So I can go ahead and put 1.5 as one of my solutions, but that means I'm going to have 2 other solutions that are going to contain the number I, which remember, I is the square root of negative 1. So let me show you how we're going to do that. Before I do, let me say that the relative maximum, there wasn't one, and the relative minimum, there wasn't one. Sometimes we have them, sometimes we don't. All right, so now the only thing left to do is to find those 2 non-real roots. What are those non-real roots? Which, by the way, always come in pairs. Okay, so the only time that these 2 number lines don't add up to 3 is if we have a double root, because we'll have to remember, hey, that actually counts as 2, which if we count it as 2, then it does add up to 3. Okay, otherwise, these 2 blanks should just add up to 3. So 1 plus 2 gives us a 3. So now what we're working on is finding those 2 non-real roots. So the way that this is going to work is since we already know one of our answers, we already know one of the roots, we're going to use that to our advantage to take a cubic function down one level and make it just be a quadratic function instead. So the cubic function that we have is 2x to the third minus 3x squared, and then plus 8x minus 12. So we're going to have to use some sort of division, whether that's long division or whether that's short division. That is that's your call. I'm going to suggest using short division or synthetic division because it's a shortcut to long division, and I like to do less work. And I could guess that you're in the same boat as me. So the way that synthetic division works is you'd only look at the numbers. Make sure that you don't have any missing terms because you'll need to use 0 as a placeholder if you do, but you look only at the numbers. So the number in front of x to the third is 2, the number in front of x squared is negative 3, the number in front of x is positive 8, and the constant at the very end is negative 12. And we are going to use our divisor. We're going to use the real 0 as our divisor. So 1.5 we already know is one of our answers. So we're going to use 1.5 as that answer. And since it's an answer, it's telling us, hey, we should get a remainder of 0. We're going to use that to break this down. So the way that synthetic division works is you always bring down the very first leading coefficient, which is positive 2 in this case. Then you multiply the divisor times what's outside the box. So 1.5 times 2, which gives us positive 3. Inside, we combine. So negative 3 plus 3, which would give me 0. That doesn't always happen, but in this case it did. Then we multiply 1.5 times 0, which gives me 0. And then inside we combine. So 8 plus 0, which would give me 8. Now this, again, is the test. Is it going to give me 0? If it is, it means I'm on the right track. If it's not, I did something wrong. So 1.5 times 8 does give me positive 12. So when I combine these together, it gives me 0. So because my remainder is 0, now I can interpret what's left as being my quadratic function. So this tells me I have 2x squared plus 0x plus 8. Now, this is why we study quadratics before we study cubics. You can solve this one of 3 ways. You can solve by factoring, you can solve by isolating your variable, or you can solve by using the quadratic formula. If you're going for the quadratic formula, you have your A, your B, and your C. Make sure that you identify B as 0 and your constant is 8. Don't switch those around. This one is a unique case in the fact that it's 2x squared plus 8. I don't need to write 0x. So one way that I could solve this, rather than using my A, B, and C and plugging those into the quadratic formula, is just isolate the variable. Use your order of operations. Use your PEMDAS backwards. So get rid of the addition first. That would give us 2x squared equals negative 8. Get rid of the multiplication by dividing both sides by 2. That would give us x equals negative 4. Get rid of the exponent by square rooting both sides. Remember, whenever you square root, you need to take the positive and negative square root. If you type this into a calculator, it's going to tell you no real solutions or non-real solutions, because we can break this apart. X equals positive or negative square root of negative 1 times the square root of positive 4. By definition, remember, don't lose track of what we're doing here. We are trying to find the non-real roots. So we knew that we're going to have the number I in this. The square root of negative 1 is by definition the number I. So we get I equals positive or negative x equals positive or negative I, and then the square root of 4, but the square root of 4 is 2. So we get positive or negative 2i. So here, 1, positive 2i, and we have negative 2i. Here are 2 more roots, 2 more zeros. They're just non-real because they contain that imaginary number I. So we're going to put those up here. We have positive and negative, so we can write it as 1, positive and negative 2i. And now we have 1, 2, 3. We have degree 3. So we have 3 zeros, we have 3 solutions, and we are all finished. You're going to do something similar for question number 6, 7, and 8. Just looking at that, question number 6, first thing I see is x to the 3rd power. And then I don't have any x squared. I don't have any x to the 1st power. So please make sure that you write this as x to the 3rd, or think of it as x to the 3rd plus 0x squared plus 0x plus 27. Do not forget your placeholders when it comes to using your synthetic division. All right, but that's just a brief overview of cubic functions. Thanks for watching, and make sure you check back next time. We'll work on quartic functions.